As we do AC analysis and we do operations in the frequency domain, we need to bring along Kirchhoff's laws so that we can make sense of circuits. So in this video, I'm going to basically show that Kirchhoff's voltage law works in the frequency domain. And what I have here is a circuit that has some voltage source, an AC voltage source. Let's put AC on it like that. And it has three impedances connected. Inside each of these boxes is an R, an L, or a C. And we're not going to show which because we're going to carry these along just as general impedances. So in AC analysis, the voltages are all cosine waves. So Vin equals some voltage amplitude times cos of omega t plus, we'll call it phi 0, some starting phase shift. So this is our input signal. Now let me label the voltages on everything else. We'll call this V1, and I'm going to label it this way here. And this will be V2. And I'll put it upside down like that, plus. And this will be V3 minus plus V3. And now that I have V1 here, let's change the name of this to V0 just so I don't get I and 1 mixed up. So we'll change that to 0. So the input source is V0, and that's that voltage. Now, when we apply KVL to this, Kirchhoff's voltage law, what it says is if we start in a corner, if we start somewhere in the circuit, let's start right here, and go around the loop, it should add up to 0 volts. That's KVL for normal DC circuits, and we're going to see how that applies to AC circuits here. So in time domain, we say that V0 plus V1 plus V2 plus V3 equals 0. So let's talk about how this is going to turn out. Well, what do we know right now? Well, we know that V0 is a cosine wave at some phase angle. Now, what do we know about the other voltages in this? In AC analysis, what we're doing is we're looking for a forced response. So we've let the natural responses to die out. There's no switch in this circuit, and we just assume this circuit has been in this state forever. So the natural response has died out. And that means we're looking for the forced response. So what we know is we have three voltages. We know that all these voltages are going to resemble the input voltage. So they're all going to be sinusoids. All the voltages here are going to be AC sinusoids because the forcing function is a sinusoid. The other thing we know, they're going to all have the same omega. The frequency of this voltage and this voltage and this voltage is going to be identical to omega here. I'm going to put a big bang there. That's really important. In an AC circuit, when you're driving it from a frequency, every other frequency in the system is the same frequency. This is a linear system and linear components. All the analysis we've done, linear components don't create new frequencies. They're all omega. Now, some other things we know. There's going to be phase shifts involved here. Remember, when we do impedance, we are multiplying by J and rotating things by 90 degrees. So we're going to have different phi for each one. And the other thing we're going to have is we're going to have different, the amplitudes of our sinusoids are going to be different. The amplitude of V1 could be different than the amplitude of V2. So this is what an AC solution is going to look like. Let's move on a little farther here. What I'm going to do now is we're going to take this input voltage plus these things that we know here, and we're going to see how Kirchhoff's voltage law works in the frequency domain when we work with these transformed Z's, these impedances. Okay, let's go ahead and do that. Okay, let's do a little more in the time domain. And we'll write out our KVL equation again. So the KVL equation was V naught cosine omega t plus phi 0 plus V1, that's the amplitude of V1, cosine omega t plus some different phase angle. We don't know what that is yet. Plus V2, amplitude of V2, cosine omega t plus phi 3 plus V3, amplitude of V3, cosine omega t plus phi 3, all equals 0. And omega, all these omegas are the same exact number, the same radian frequency. All the phis are different, and all the V2s and V3s are different. Okay, now I'm going to switch to complex exponential notation. We're just changing notation here. We could represent this number here as, this is the real part of V naught, V0, e to the j times omega t plus phi 0. That's exactly the same as this. This cosine can be represented as the real part of a complex exponential with this frequency. And I can write out the rest of these. V1 e to the j omega t plus phi 1 plus the real part of V2 e to the j omega t plus phi 2 parentheses plus V3, real part of V3 e to the j omega t plus phi 3 equals 0. All right, now, one thing I can do next, we can start to factor this. We can start to take this apart a little bit. So I know that if I have the expression, e to the j omega t plus phi, just in general, I can change that, but just by exponent properties, to e to the j phi. Oh, let's get the parentheses in there, like that. E to the j phi times e to the j omega t. So I'm going to do this transformation on all four of these terms here. Let's keep going. So we're still working on this. Let's go. The real part now, I'm going to take apart omega t and phi 0 here. And I get V naught e to the j phi 0 e to the j omega t plus real part V1 e to the j phi 1 e to the j omega t plus real part V2 e to the j phi 2 times e to the j omega t plus real part V3 e to the j phi 3 e to the j omega t all equals 0. And here's a nice simplification. We take out this common term. We're going to factor out this common term across the entire equation. And what do we come up with? We come up with the result is the real part of V0 e to the j phi 0 plus V1 e to the j V1 plus V2 e to the j phi2. See the pattern? All that times e to the j omega t. And we close that, and that equals 0. And we're getting close. We're getting close. All right, how do we make this equation 0? Does e to the j omega t ever become 0? Well, e to the j omega t is a rotating vector. It's never 0. So that's not going to do it. So how do we get it? Well, that means that this other term here has to be equal to 0. So how am I going to do that? I'm going to make one more notational change. This kind of a number here is called a phasor. It's some amplitude times e to a complex 1 angle. And there's no time up here. There's no time. The time is only over here. This is the only place that time appears in the equation, and this is the only place that omega appears in the equation. And these are just phase angles. These are starting phase angles. So my notation for a phasor is going to be, I'm going to call it V0, and I'm going to put a line over it to indicate that it's a complex vector. And that equals V naught e to the j phi naught. So when you see the vector symbol and the ought, that's that right there. And we can write now, finally, the real part of V naught plus V1 phasor plus V2 phasor plus V3 phasor equals 0. So this is KVL in the frequency domain. And fortunately, it looks exactly like KVL that we remember from our DC analysis. The sum of the voltages going around the loop is equal to 0. And in this case, it's the sum of the phasors going around the loop is equal to 0.